Welcome back. Let us continue our discussion with unsteady state situation of fluid flow. It's a very simple situation here. We have a fluid in a cylindrical pipe at time t equals 0. The flow is started by maybe applying a pressure drop across it, and we are interested in the time it takes from time t equals 0 to the time when steady flow is achieved. So we are looking at the unsteady region, and we are trying to get some insights into that. We arrived at this differential equation in terms of the non-dimensional variables that we had defined. Dou phi dou tau equals 4 plus 1 by xi dou xi dou phi dou xi, and the initial condition and boundary conditions were written in terms of the non-dimensional variables. We took a break at this point and we said we'll continue with the solution here. It is tedious, and therefore we are doing it in parts. So here we know that the velocity for steady state flow in a pipe is something like this. We already know this from our earlier derivation. Vz equals minus delta p r squared by 4 mu L 1 minus r by r squared. Okay, the parabolic velocity profile that we got for laminar flow in a pipe. So this is the steady state velocity profile. So from the definitions of dimensionless variables phi and xi, we can write the above steady state velocity as some phi infinity equals 1 minus xi squared. Okay. This is the value of phi at infinite time for the purposes of this situation is 1 minus xi squared. You can see how this works. R by r is xi, and the remaining actually turn out to be phi, and we're calling it phi infinity because it's the ultimate. It is reaching steady state at the end of, or in terms of at infinite time for this particular view. Phi infinity equals phi at tau equals infinity when steady state is reached. This is equation 3.5-7. Now, this is the standard trick that is done. This phi can be written as a combination of a steady state value and a deviation value. Nothing prevents us from doing that. Okay. The non-dimensional velocity at any point is some value plus or minus a certain deviation. Okay. This is a standard approach that is taken. So let us do it this way. So phi of xi tau as a function of xi and tau, which are non-dimensional distance, non-dimensional time, is phi infinity at xi, this no longer depends on tau, minus phi at a certain t, which depends on xi and tau. Okay. So a steady value and a deviation value, here it is given as a negative, whatever, negative, positive, whatever it is. Okay. That doesn't matter. Typically taken as negative for the formulation. Steady state value, the deviation value. We'll call this equation 3.5-8. Therefore, dou phi dou tau can be written as dou phi infinity minus phi t divided by dou tau. I'm just writing phi in terms of phi infinity minus phi t, which is nothing but negative of dou phi t by dou tau, since phi infinity is not a function of tau. Okay, so this is pretty much a constant as far as this is concerned. Therefore, we have taken something, okay, don't worry about it. We have brought it in terms of a fluctuation variable minus dou phi t dou tau. Further, 1 by xi dou xi dou phi dou xi. This is the term on the right hand side apart from minus delta p by L. This can be written as 1 by xi dou xi. Phi in terms of phi infinity and phi tau, phi t is dou phi infinity minus phi t, the rest remaining the same, and this is nothing but 1 minus xi squared minus phi t divided by dou xi. In terms of the non-dimensional variables, phi infinity is 1 minus xi squared. I think that we already saw here, right? Yeah, phi infinity is 1 minus xi squared. Okay, this is what we are using there. Equation 3.5-7 into that. And therefore, this can be written as 1 by xi dou dou xi, the xi is following us. And this derivative, now we have it in terms of xi and phi t. So, 1 is a constant, does not depend on xi, minus xi squared is 2 xi, and this is minus dou phi t dou xi. Okay. So, this is what we have converted it as. So, that can further be written as this 1 by xi dou dou xi of minus 2 xi squared, I have taken xi inside, minus xi dou phi t dou xi. Okay. So, now if you differentiate this, we can get 1 by xi, dou xi is what we are trying to do to this, minus 2 xi squared, therefore minus 2 xi cube by 3, you manipulate that and so on and so forth. You're differentiating it here. I'm very sorry. You're differentiating it here. So xi squared derivative is 2 xi. So minus 2, 2 minus 4 xi. And minus d xi of xi dou phi t dou xi. Okay. Here we're just keeping it as the same. So we get minus 4 minus 1 by xi dou dou xi dou phi t dou xi. So you substitute in equation 3.5-6, which is this, right? The earlier thing that we saw. Good to keep checking. Yeah, this was 3.5-6. Dou phi dou t is 4 1 plus 1 by xi dou xi dou phi dou xi. We have written it in terms of a steady state variable and a deviation variable. Now we are rewriting this equation in terms of the deviation variable. And that whatever remains of the steady state variable, inside the derivative it's going to, it dropped out. We get minus dou phi t dou tau equals 4 minus 1 by xi dou xi dou phi t dou xi. This way we have gotten rid of 4 minus 4, that cancels out. So now we have it as this form, dou phi t dou tau equals 1 by xi dou xi dou phi t dou xi. We'll call this equation 3.5-9. Okay. We have successfully reduced that to this form. Now the initial condition is at tau equals 0, phi t equals phi infinity. Okay. Because there is no flow, there is no fluctuation. There's only a steady value which would be 0, and at xi equals 0, phi equals finite, since phi infinity equals 0. Okay. And at xi equals 1, at the wall, phi t equals 0. Okay. This is the second boundary condition. If we take this phi t of xi and tau to be separable as a function, as a product of two functions, one being a function of xi alone, the other one being a function of tau alone. This is what is meant by a separable case. If we take that to be the case, then dou phi t dou tau equals f times dg d tau. Okay. We are taking it as separable because we can write this in terms of the total derivative. Dou phi t dou xi is a g times df dxi. Okay. Therefore, we put it back, we get f dg d tau equals 1 by xi d dxi xi g df dxi. So we have converted this into a total differential equation or an ordinary differential equation. So some more manipulations, f dg dou d tau equals g, I have just taken g out, 1 by xi d dxi xi df dxi. So bringing it to this side, 1 by g dg d tau equals 1 by f. I'm just separating out the variables, equation 3.5-10. And now you find that left hand side is a function of tau alone and the right hand side is a function of xi alone. We have finally attained that situation. That is the case, both have to be equal to the same constant. And we are going to call that constant as minus k squared. Okay. There's a reason for this, it will become apparent in the next few steps. but just be with me here. It's minus k squared. So 1 by g dg d tau is minus k squared, equation 3.5-11, and therefore g equals C1. This is the solution, right? dg, you have a ln g, and you have minus k squared t here, and since you have a ln, you get g equals the constant, the exponential term, and this is the constant of proportionality. That's it. So this we call as 3.5-12. And now the reason becomes clear. G and consequently phi t can diminish to 0 at steady state at tau equals infinity only if minus k squared is not negative. Thus the constant minus k squared needs to be negative. Okay, so that's the reason why we took a k squared term, which is always positive, added a negative to it, and we took that to be our constant to satisfy a physical situation. Reading it again, g and consequently phi t can diminish to 0 at steady state only if minus k squared is non-negative from this. Thus, the constant minus k squared needs to be negative, and this form minus of a positive number, a square, will ensure that it is always negative. Equation 3.5-10 can be written as 1 by xi d d xi, xi df d xi plus k squared f equals 0. That's the other side. And the boundary condition 1 at xi equals 0, f equals finite, therefore df d xi equals 0. And at boundary condition 2, xi equals 1, when at xi equals 1, f equals 0. Since phi t equals 0 for all g, okay, since g is a function of tau alone. Now, the solution of this needs a knowledge of Bessel functions, which you would have seen in your math course. I'm not going to go into detail of Bessel function. If I get into that from a very preliminary point of view, that's an entire course by itself. So I'm not going to do that. This happens to arise in this situation. Therefore, I'm just going to draw from mathematical relationships of Bessel functions just in the context of this solution to give you the solution. Okay, that's what we're going to do. If you want to better understand it, you could read books like this, Lee, M.M., 1974, Transport Phenomena in Medicine and Biology. It's a nice book. This gives you a lot of detail. You could read this book to get more insights about Bessel functions, or you could look at books on Bessel functions to know more about Bessel functions. Okay, the whole entire field there of Bessel functions. Here we are going to merely present the solution. The solution is of the form f equals c2 times a function plus c3 times another function. Equation 3.5-14, where this j0 is called the Bessel function of the first kind, which is defined as this. For example, the Bessel function of the first kind j0 of k xi is sum of k going from 0 to infinity of minus 1 power r k xi by 2 raised to the power of 2r divided by r factorial square. Okay, so this is the Bessel function of the first kind, and y0 is the Weber's Bessel function of the second kind, which is defined as y0 of k xi equals 2 by pi y0 dash of k xi minus ln 2 minus gamma times the Bessel function of the first kind of k xi. Okay, where gamma is the limit n tending to infinity of 1 plus half plus 1/3 and so on till 1 by n minus ln n, and that happens to be the Euler's constant 0.57721. So we have taken care of this. y0 dash is the Neumann Bessel function of the second kind, which is defined as the Bessel function of the first kind times integral d xi by xi, the Bessel function of the first kind squared. Okay, we're just taking this on face value, going just follow this in terms of what it turns out to be. I will not expect you to solve this in any aspect, that requires solutions in this course, but this is what it involves. You need to know that. Now C3 equals 0 from boundary condition 1, otherwise the term would not be finite, and therefore C2, the Bessel function of k, of the first kind of k, equals 0, and C2 cannot be 0 since that would result in a trivial solution f equals 0. If you want, you go and I'm just going to present this. You can go and work out the logic in your own time by understanding Bessel functions. Therefore, the Bessel function of the first kind of k equals 0, and this will happen multiple times when k equals 2.4048, equals 5.52009, and so on and so forth. Thus, there are infinite solutions, and Fn equals C2n J0 of Kn xi, n going from 1 to 3 till infinity. Implication is that phi of Tn equals Cn dash, Bessel function of the first kind of Kn xi, exponential of minus Kn squared tau, n going from 1 to 3 till infinity. Equation 3.5-14, where Cn dash is C1 times C2n. And using the principles of superimposition, orthogonality relationships, and other relevant aspects of Bessel function, the final solution will turn out to be phi of xi tau equals 1 minus xi squared minus 8 sum of n equals 1 to infinity, Bessel function of the first kind Kn xi divided by Kn cubed, Bessel function of the second kind of Kn exponential of minus Kn squared tau. Okay, so I've just read this out. I don't expect you to do this on your own and so on and so forth. We are not going to, none of the solutions would need you to manipulate on these aspects, but this is the way the solution comes. You need to know at least the basis of the solution and the complexity of the solution. 3.5-15. If you plot, this is a solution here, you have phi as a function of xi, that's what we are looking for. If you plot that phi as a function of xi, this is valid for any radius, any viscosity, any density, and so on and so forth, at various taus. This is 0.05, it will be something like this. At 0.1 tau, it will be something like this. 0.15, it will be like this. 0.2, it will be like this, and so on, till tau reaches infinity. You get to your parabolic velocity profile, which is the steady state velocity profile in laminar flow, well developed laminar flow in a cylindrical pipe. So that is what I have for you here. Unsteady state, I wanted to present something so that you have an idea as to what it is. Don't worry about the mathematical complexity. You will not be expected to do manipulations at the Bessel function level in this course. Okay, but you need to know what a Bessel function is. And for those of you who are comfortable with it, please go ahead. Please get more insights into it and so on and so forth. Okay, please do that. Let's stop here for this class. We are out of time, out of patience, I suppose. A lot of rigorous aspects, some of which we had to do blind because of the level of information that is needed. There's a lot more than a basic manipulation level. Okay, let's stop here. Let's meet in the next class. The next class also promises to be math full with us looking at pulsatile flow. Again, I'm just going to give you some insights. I'm going to let you figure out by drawing what the profiles are going to be and so on. Okay, but you need to know this. All these are very relevant. The unsteady aspects happen in a lot of disease situations and so on. So in the arteries, you need to know about it. See you in the next class. Bye.